Oh, here we go. Welcome back, everyone, to the Cyberbot Educator Workshop with Python and the Microbit, day 2. Let's see here. I just moved a few slides around and looks like I got myself in a bit of trouble. So let me see about correcting that. Okay, here we go. So for anybody looking along, if you want to if you want to have the slideshow open, here is the short link for watching on YouTube, or the QR code for checking on your mobile device. And I will again paste in the official link to the slideshow into the chat. Paste. There we go. All right. So yesterday we did kind of a sprint through centering our servos, because I went a little bit too slow during the first half of the workshop. So I wanted to just first of all show you, I think there was a question that came up, where are these instructions for centering the servos? And they are, if we back out and then go to Cyberbot, Cyberbot tutorial series. So that we started actually at learn.parallax.com. That's this. Then I clicked Cyberbot, Cyberbot tutorial series. So this is the student workbook right here. And build your Cyberbot is where we're at. We've gone through software setup beforehand, writing microbit programs beforehand, and then reiterated at the beginning. Add modules to your microbit. So those are the 3 that we did last time, plus part of this 4th chapter here, which is we went through identifying your Cyberbot, which is right here. And there's a link to the Rev B instructions if it turns out that you have a Rev, or that your class has a Rev B Cyberbot board. For Rev C, we did talk a little bit about, hey, this is the Cyberbot board. It has all these nice things like holes to attach to a chassis, a little battery power jack, place for a speaker to go, servo ports, low battery indicator light. This flashes red if your batteries are low when you start up the robot. Let's see here. We have a breadboard. Around the breadboard are electrical supply and connections to what are called I/O pins. I'll go further into that later. And then we've got a 3-position switch. Position 0 is all off, except for the microbit. If it's plugged into a USB cable, that'll still run. Position 1 allows you to run scripts that talk to sensors on this prototyping part of the board. Whereas if you put it into 2, it also adds in power to the servo port. And the reason we did that is because it's often convenient to have a program that both displays sensor data and makes the robot go. And so in position 1, you can be displaying the sensor data without having the robot make any maneuvers. Then you put it in position 2 and off you go. Then connect the microbit to the Rev C board. You saw this on Monday. And then last but not least was the center the servos, which I kind of took everybody through out of memory. These are the step-by-step instructions. And so note that it shows things I didn't mention. You can use a little jumper with 2 sockets and slide it over the lower pair of pins to give the servo regulated 5 volts, or the upper pair of pins to give the servos power straight from the batteries. We go with 5 volts because we're using alkaline batteries. If you have some good high capacity nickel metal hydrides, you can go ahead and put that jumper either on 5 volts or VN. VN gives you a little more speed. That's kind of nice. Talks about the 3-position power switch. Shows how to get everything connected. along with some close-ups so that you get the white wire closer to the edge of the board. And this is what it looks like when it's done. This is the script to center one servo. And then we give you a script to center the other servo. And one thing I did was center them both at once. Okay, let's see. So are there any questions about that before we move on to today? All right. As always, feel free to jump in if you're stuck or if you want to ask a question. Just unmute yourself. We've got a group of only 30-ish or possibly fewer. And so should be pretty manageable. Did everybody find the nice little wrench for putting together your, we feel that that's kind of a necessary item. And there is an important instruction in the tutorials that shows how to see if I can find it. Make sure your students don't miss the little animated GIF file that shows how to put the nylon lock nut into the closed end of the combination wrench. Okay, then. So today we'll do some review and questions and answers. I think I just got through the review. Then we'll do some scripts for navigation, followed by a discussion about circuits. I feel pretty confident that everybody can go through those and follow the instructions. So we're not actually going to do any hands-on circuits before we build our first sensor circuit. Just know that there are some circuit tutorials that come before we build our first sensor circuit for navigation. And I'll show you those, but we're not going to go through it in the interest of time. We'll take a look at navigation with light, and then for homework, we'll actually either have you try some of the circuit projects or do light sensing. I need to update this, but basically, yeah, we'll do, if you're comfortable with circuits, try the light sensing project. If you're new to circuits, we'll have you do some of the beginner stuff. And if you have time and are so inclined, also try the light sensing project. And that'll be your assignment, along with making sure you can log in to our learn.parallax.com site so that you can get to the assessment materials, which we will talk about on Friday. So questions and answers, I already talked about where the instructions are for centering the servos. Then there was a question that came in over email. Hey, there's a whole bag of circuit parts. Am I supposed to be building anything on there? The answer is no. We'll start doing that today. And then for optional homework, you can build stuff on there between today and Friday. And then my question for you is, can you all get set up with, hopefully you all downloaded the adjusted hex files that I sent out, because I made a mistake, and let's talk about that briefly. Okay. So what you want to do is, once you go to python.microbit.org/v/2, hit load save, and then or browse for a file is where you open a file. And then let's just take a look at center servos that we worked with. Okay, so I made a mistake, and I wasn't really listening to everyone about that mistake. I had the 22 pin, which is called out at the bot object level, inside the param or the arguments for the method call, like that. And we were all getting errors from that. And so what we want to do instead is have it like this. And if I could get everybody to open your Center Servos script and then hit load save and check and make sure in your files area that you do have Cyberbot Pi in there. That's going to be important because we're starting to use it, or we're going to continue using it today. So can I get some thumbs up when you all have, thank you, Alan, Marcel, good job. Let's see some more thumbs. Excellent, Brian. Josh, good.
I'm getting an error. It's saying no space available. I just lost the error. It says could not add file to there's no storage space left.
Okay, so was that when you loaded the script in?
Yeah, I tried to add file right under project files. Is that where it's going? And yeah, let me try a different browser. You haven't seen that error right before?
Well, okay, so the first thing is it has to be a Chrome browser.
Yep. Let me
Okay.
Chrome.
And then, so we usually see that when it's a very long script, or if maybe.
Oh, you know what? I was doing the hex file. We're supposed to do the Python file. Is that right?
Oh, wow.
That's what
hey, that's cool. I've never seen
when you
that
said
before.
Long file, I realized, oh, that would have extra stuff in it.
Yeah, because the hex file has a lot of extra stuff in it. Yeah, it should always be the .py file.
Okay.
That is added to the project. So load save or browse for a file. And then we want to add, go into Cyberbot MicroPython.
There's also another way you can add project files. You don't have to drag it over, but if you go down at the bottom, you can add the files at the bottom.
Yeah, and you can actually, because of some text that we have inside the Cyberbot okay, so for this, I'm going to go into try the beta. Don't follow me here, folks. Just watch. What I'm going to do, this is the beta editor that will eventually become the Microbit v3 editor. And we can open a hex file here and open Center Servos into it. And so it probably looks normal, just like Center Servos. But if you go down in the lower left here, there's a project button. And when you hit that, you can actually see main.py, and you can also see cyberbot.py. Now it's trying to protect us all from students editing this module. And so you actually have to go into settings and allow editing before it lets you into it, but you can actually see the code. And what happens is if you drag and drop this into a project, because of the way the name is set here for Cyberbot at and then a version, this will actually go straight. You can actually drag and drop it straight onto your project, like one of these projects, and it'll just automatically add it as a module. And then this is very difficult code to read. And one of the reasons is because unlike C language, Python is going to bring all your, MicroPython will bring all your comments and all the characters of the script into memory. And so we wrote this to be as concise and not verbose as possible. On that note, well, so remind me to, no, I can do this. Okay, so going back a little ways, this is slide 49, and the slides move around as I add and remove slides for each new workshop. But if you search for cyberbot.py module contents, you'll get to see the different method calls that you can make with your Cyberbot module. And so, for example, here is servo speed. We'll be using that one today. Here is servo angle for if you add a standard servo that turns to and holds an angle. You can also send tones to the speaker that's on the Cyberbot. There are also options for version 2 microbit to just send tones to the speaker on the microbit itself. And there's lots of others here. Don't want to spend too much time talking about that. Otherwise, I'll end up whizzing through a bunch of material again at the end of this workshop. So with that said, are there any questions before we move on to navigation?
I have a quick one, Andy.
Yes,
With
please.
regards to- I know we're not there, but as part of the sample, you had the bot22.tone. Is that only going to function with a Piazza,
Well,
which is not currently attached to the board? I mean, I can
yeah, no, that's just a simple frequency output. So you can actually select a frequency that's in the radio spectrum and stick a wire to it and get a super high frequency. But that would only be true for the Cyberbot board. The Cyberbot board has a microcontroller that's capable of broadcasting or sending uber high frequencies. The microbit itself doesn't go quite as fast. Okay. Okay, so here we go into navigation. So this is the navigation page on the Learn site. And just a quick heads up that if you want to go to that navigation page from the slideshow, you can click the title here and then click the link that appears below it, and it'll take you straight there. The same applies for the actual page. That's the same link. And then we've got links here for the table of contents, at least at the top level. There, some of these have sub activities or sub links. So first question, or first thing we want to check is to make sure that our servos are still centered. And for that, we'll go ahead and run this program right here. Connect. Select your microbit. And then hit connect. Then download turns to Flash. Now that it's Flash, we can hit Flash. And it'll load the script. And let's see here. I actually forgot to get the camera on the robot here. All right, so here we are.
Is the wheel considered I call it the ball wheel, the front or the rear?
It is,
know it can
we
be
call
either.
it the tail wheel. This is a tail dragger, like those old biplanes that we see in World War I movies, and used to be crop dusters that were that way. Okay, yeah, the tail wheel. So this is the front of the robot. This is the back of the robot. And now it's not doing anything because I have the 3-position switch here still set to 0. And the important thing is we want it to not move when we move the 3-position switch to 2. Because right now it's sending the center stay still signal to both servos. The first thing I'd like to do is check and make sure that we all have our right wheel connected to the port on the right, which is, can you see that there? It says P19. So P19 is the port on the right, and then P18 is the port on the left. And one way to figure that out is simply to set the speed for the P19 servo and make sure that this wheel right here goes. And by the way, if you very gently try to turn the wheel, you will feel it resist against your manually turning it, especially if you turn it clockwise. It's going to push against you a little bit. And so this is a little bit risky way to have my robot sitting, but so what we're all doing, oh, first everybody please make sure that your breadboard is forward on your robot, just like the wheels, the drive wheels are forward. And then this wheel back here is the tail wheel in the back of the robot. If you have it on backwards, pop all these 4 screws right here and turn it around. Let's see here. Okay, so now what we're going to do is we're going to make sure that if we just control this wheel, that it will that this wheel will turn and not the one underneath. So either if the one underneath tries to turn, my whole robot's going to start moving. If this correct one on the right side of the robot turns, then I know I have the servos correct. And I have a 50-50 chance of having this go right or wrong, depending on whether you're an optimist or not. So all you have to do is comment out the bot of 18 call. And then let's give a nice slow servo speed of 25. That's 25 out of roughly 100, although you can go all the way up to 200 to squeeze every bit of top speed out of the servo. Okay, so once you've done those two things, so we're commenting out the bot of 18 call by using a hashtag, and then we're setting the servo speed of the P19 servo to 25. And then we'll go ahead and flash it. And let's see what's going to happen here. Oh, look at that. I did it wrong. Okay, so notice that the wheel underneath the robot is turning. And so my robot is trying to kind of rotate in place. So if that happens for you, all you have to do is set the power switch back to 0. And then unplug these two servo cables and swap them, so that the one that was in 18 goes into 19 and vice versa. Okay, now when I turn the power back on, nothing at all happens. If that occurs for you too, there's that reset button by the serial cable underneath the microbit. Just press and release that. And now I have the correct wheel turning, and it's turning counterclockwise. How is everybody doing with this? Have you all got your right wheel turning counterclockwise? I'm seeing a few thumbs and nods. Remember to break in and say, give me a minute or 30 seconds or 5 minutes, whatever, if you need to make that adjustment. All right, now what happens? What do you think will happen if I change this from, I think I'd better brighten up this.
It'll go backwards.
Well, depends on if I make it negative or if I do something else with it. Let's see here. Whoopsie, that's the wrong one.
Hey,
Ducam.
Andy.
Yes.
Hey, I don't mean to interrupt, but when I go from the third position of the switch to off, I swapped my servos and cut it back to the third position. Should it start running again, or do I need to download the code again?
Well, downloading the code again will have the desired effect, but you can also just press that little press and release the reset button that is underneath microbit. See the to the left of the to the USB cable underneath the microbit, there is a reset button right there.
Okay. So it when you turn the 3-position switch off, it loses the command, so it needs to be restarted. Okay. I'm with
Well,
you.
yeah, what happens is with the USB cable plugged in, that's what happens. When the USB cable is not plugged in, basically when we turn the power to 0, what happens is that the microbit loses communication with the microcontroller that is right there. Oh, sorry. There we go. Trying to get it at the right angle. Okay, so right here is a microcontroller that the microbit is forwarding those commands to. And when we turn power off, the microbit is still awake, but this guy isn't. And turning power back on, in order to have them restart their conversation when the USB cable is connected, you'll need to press and release that reset button. And then
Okay, thank you.
you're welcome. Let's see, and this looks a bit upside down.
Okay.
I just can't get this to go. I'm gonna have to work upside down with you guys, I think. There we go. That looks all right. Does that look right side up for everybody?
Yes.
Okay, excellent. All right, so can you see how fast the servo is turning through the video? Okay, excellent. So here we have 25. Let's change that to 15 and reflash the code. Is it turning a little slower? You can try 10 if you want. So for me, that's turning significantly slower than 25. Let's try going up to, or let's try going now to -10. So after trying 10 and noting that it turned slower, remember now we're counterclockwise. Let's guess what's going to happen if we do -10. My hypothesis is that it's going to go roughly the same speed, but in the clockwise direction. But for me, nothing happened. And that's probably because of the way I centered the servo. It's probably a little off from exact center. So maybe we'll try -20. There we go. Okay, how about everybody else? Have you got the clockwise slowly now? Okay, so let's try -40. Is it going faster?
Yes.
Okay, we'll go -60.
Ellen is asking for the value you need for ludicrous speed for those ludicrous speed for those Spaceballs fans out there. It's Mel Brooks movie.
Oh, I don't know that one.
But honestly, what's about the maxis will go over what value you put in there? Is it just not going to change anymore?
Okay, so that's a really good question. And to answer that, we'll go to the slides and take a look at this little graph right here. So this little graph shows the speed setting that I'm using along the bottom. So these are numbers that we could put in that method call.
As a
Eh,
percent of full speed?
More or less, really full
Okay.
speed. If we look at the graph, hold on let's hold that question for just a second.
Okay.
So here we have 0. So when we have our speed, when we use bot of what is it, 19? Yeah, bot of 19, servo speed of 0. We get 0 RPMs out of it. Now, when we give it, what do we have, like 25 or something like that, 20? When it's positive, we have a positive or counterclockwise, for our convention, number of RPMs. If we give it a smaller number, we have a smaller positive number. If we give it a bigger number, like 50, we'd have a higher number of RPMs. Now, to get up to the neighborhood of 50 RPMs, what you want to do, if you want to give it as much speed as possible, that ludicrous speed would be 200. Linear control occurs up to about 100, maybe a little over. See how it kind of levels off, but still increases little by little up to about 200. So really, practically, I would say like 120 is going to be our top speed, and negative 120 for the clockwise rotation. And it's the same deal here. You know, when you've got 50, you're at about half speed clockwise rotation, maybe negative 30 RPM. And then when you're up to 100, you're near full speed at negative 50 RPM. So we can try that too. We can go all out here. So first of all, I'll try positive 200. That should be full speed in the counterclockwise direction. So it's going to be turning this way very rapidly. I don't know if that images very well on Zoom. And then negative 200 would give us full speed clockwise. But negative 125 is not going to be really different from full speed clockwise. It's still going about full speed. But if we drop it down to half of 125 would be 62.5, but we'll round it to 62. If we flash that, you should start see it going noticeably slower. And then if we have it again at 30, we're definitely in that linear speed control range. And there we go. Probably slow enough now to be visible to the Zoom video. And then dropping it to 15, it's going to go even slower and so on. And then the same applies in the reverse direction. So we can do that same game with the positive values starting at 200. And one of my plans for these tutorials is to add a chart that the students fill out. So that they get a feel for counterclockwise versus clockwise, and then how linear speed control goes for the motors. Okay, are we all okay with that? Feel pretty good about, positive speeds. The larger the number, the faster counterclockwise. Negative speeds, the larger the number, the faster clockwise. All right, so now it does get a little tricky when we think about the servo direction. So I should have been pasting these. Okay, so first of all, I do see a typo here. I did notice this. I need to also fix this because the 200 is what gives us these pulses that last a certain amount of time. So basically, if you had a light connected to the circuit and you had a super fast camera, you would see the light go on for 1.3 milliseconds. and then turn off. And for 20 milliseconds or 20 thousandths of a second, light stays off, and then you get another on for 1.3 milliseconds. So that's our negative 200. And then our positive 200 would be the 1.7 milliseconds. And that goes to the white wire of the servo and makes it turn. And so here is in the tutorial how they're having us try out 75. And making it stay still, making it turn clockwise. So that's what the students go through. It's a little different from what I showed you. Next up, here's a tricky thing. So if we look at our servo here, give it negative 20 for some slow clockwise motion. So what direction is that going to propel the robot?
Forward.
Forward. All right. If we turn the robot around, what did I give it just a second ago? Was it negative 20 that I gave it?
Yep.
Negative 0 is probably not a real number. Okay. So now we're looking at the other side of the robot.
Upside down.
Thank you.
And that would be going backwards.
Yeah. So the same value on the other side of the robot does not give us forward. It gives us backward. And so if we want the robot, I'm going to set the power switch to 1. So I just set it to 1. That leaves it on, so I don't have to reset the microbit. And now what I'll do is set us to forward by taking 19 and giving it 20 and 18 and giving it negative 20. Now this is not going to be a great forward because of how centering is not a perfect process. And I prefer to have the left servo come first. Uh-oh. And then the right servo. There we go. So I prefer to have it like that. So this should be forward, but it's probably going to curve quite a bit. So let's try that on the ground. Okay, now I still have the switch in position 1. It's not going to start moving until I set it to position 2. Uh-oh. Why is it going backwards? I must have really flubbed it. Let's see here. 19. Oh, yeah. 19 is the right servo. I had it completely backwards in my mind. Sorry, everybody. I think if I'd have been going from the written instructions a little bit more, I would have done that right. Okay. So 19 is the right servo. The right servo needs to be turning clockwise. 18 is the left servo. The left servo needs to be turning counterclockwise. I'll paste this into the chat.
I still go back to that.
And chat. Paste. Okay, so that's the script you can paste in if you want. And it's going to curve quite a bit, probably, especially given that one side moved at 10 and the other didn't. So I'll go ahead and set mine to from 1 to 2, my power switch. Oh, I forgot to load the modified code. Just a second. Slash. Again, my switch is in 1. Now I'll move it back to 2. Okay, can you see how it's turning a little bit? How the left wheel is turning faster than the right wheel. And so it's turning to the right. So to get it to straighten out, we'll either want to slow down the left wheel or speed up the right wheel. Since students always like to make stuff go at top speed, I prefer to slow down the faster wheel because when you're going at top speed, you don't have the choice of speeding up the slower wheel. So again, that's the left wheel that we need to slow down. And so let's try, I'm going to try 15 for mine. You'll need to, and if yours is turning left instead of right, you'll need to slow down the other wheel. But so now that I've got that, that left wheel slowed down a little bit, let's see how we do. That's a lot better. So can I get, I'm interested if that's more inherent to the motors or more inherent to just the way I was turning my screwdriver when I centered the servo. Can I get some comments on whether all your bots were turning to the right, going this way? Did anybody have their bot going to the left?
I wrote some different code to do a test to get my robot to basically spin on a 270 degrees one direction and then come back 270 degrees by just inverting my numbers to just get a sense of accuracy. And I'm just using 25 and negative 25 pairs of positives, pairs of negatives in order to get the rotation. And it does not return to the same spot by a fair number.
Well, and one of the reasons for that, I believe, is because of the fact that when it reaches the end of its motion, it decelerates and then accelerates. And so going for the same amount of time does not get you back to the same position. Let's get to that later.
No problem. That's okay. I'm following. Got it.
Okay.
I just had a quick question. I just want to confirm again. So what we call the front of the robot is the two wheels.
Yes.
And the back is the, okay.
Yes. So, let's see, here is a graphic from the student workbook. It's not zooming very well. There we go. So this is where we start off with. And then I believe, does it repeat it here? No. Okay, so we talk about what the direction is right at the very beginning of the navigation chapter. Okay. So next up, let's try making it go forward, left, right, and backward. I'll go ahead and do the code. Wait a minute. I think I might be able to just get some code from the student workbook on this. See what we have. Okay, forward and backward. Okay, here is forward, left, right, backward. And I'll first give you the page link. And then give you the actual script. And again, this is where to really learn it, you'll want to hand enter the code, but to get through the workshop, we'll have to use the copy and paste method. Be careful to select everything before pasting in. I ended up pasting where my cursor was without deleting everything first. So I have two programs in here. That is likely to happen to some of you too. So now I've done my code surgery and we have just the most recent program in here. And so when we flash that, now, because I have it on 1, it's not doing anything. And if I turn it to 2, it'll actually start somewhere in the middle of the program. So with this one, what we'll want to do is press and release that, is set it to 2, and then immediately press and release the reset button underneath the microbit. So set to 2, press and release reset. And there's forward, left, right, and backward.
And
And
you
then
don't have to have the cable connected anymore after you put the program in it, correct?
That is true. For example, I can disconnect the cable. And once the cable's disconnected, when you turn power off and back on, it'll go ahead and repeat the same program. Now, I don't know why I've got one of the wheels turning. I'll have to take a closer look at that. They should not be turning.
Maybe something is no longer centered.
Your
Well,
phone has a extra servo motor -20 at the end. Is that the reason why?
you know what that is? I don't know why that's in there. Oh, you know what? That was another remnant from my previous, thank you, good eye. That was a remnant from the previous program because I didn't delete the whole previous program before I pasted it in. I thought it was all up top, but there was that one stray statement at the bottom. So. So power to 1. Now I have to reconnect. So I had to hit the connect button, select my microbit again, confirm the connection, flash it. And at this point, sure, we can go ahead and disconnect that. You need to hold the microbit into its socket as you disconnect the serial cable. Then you can turn power off, then move it all the way to 2, and it'll repeat its dance. Okay,
Slightly off topic.
go ahead.
I switched the ports that for the left and the right, and then adjusted the code. And when I did that, the port that was lower had the higher speed. So it may be a slight voltage variation that's causing it between different ports.
Well, that is possible. Another possibility is simply that if we go back to the centering diagram here, this has a fair amount of slop in it because of the way we centered it. There is an alternate way that I might put in the updates to this chapter where you have the wheel turn back and forth and you use the screwdriver to fine tune the adjustment so that it turns the same distance back that it turns forth. What that does is it makes this deadband area where it doesn't turn at all, because it's about 12 microseconds wide. So 12 millionths of a second. And then the servo speed, each increment here in servo speed is 1 millionth of a second for how long these pulses last. And so that could have some effect. Also, there may be some asymmetry in the overall speed response of the motor. And so those are all things to think about, but at the end of the day, what we want to do, and what I'm hoping you'll have your students do, is just have them make sure they pick values so that they'll see 75 and negative 75, but they'll have tested and put in their values for actually straight forward and actually straight backward. And so just a quick thing here, notice that for forward, we have 75 and negative 75. And then for backwards, it's the reverse. It's negative 75 and 75. To pivot in place, we're turning 75 and 0. You could also do that to make it turn in place instead of pivoting on one wheel. So this is pivot on one wheel because one wheel stops. And then this would be both wheels turning counterclockwise. And so that the robot will rotate in place. All right. Oh, I guess I got a little bit ahead of myself, didn't I? So this is the rotate in place slide. And by the way, all of these slides that we've been doing, with the exception of this one, which isn't in the tutorials yet, but I kind of have my eye on that, have links at the bottom to show where the image came from in the student workbook. Wherever possible, we want to, I want to be showing you stuff from the student workbook. And if I end up showing you stuff that's not from the student workbook, it probably means I should add it to the student workbook. So yeah, so here we have the various maneuvers and where they are in the student workbook. And so this is kind of the same thing. Now let's try real quick going forward and to the right. And you may need to adjust, if you want it to go perfectly forward, you may need to adjust those forward numbers. Here's the script. Probably should have run it first to make sure that it worked right. And I copied everything, but guess we'll just go Maverick here. I'm going to slow mine down a little bit. Oh, actually, it should have been 15 and 20. It's going to curve. And okay, so the left wheel is positive. The right wheel, I believe those were the numbers I had. Yeah, so it's going forward and then it turns. Now, if you want it to go further at a given speed, you can change the time it sleeps between changing the maneuvers. So this sleep 2000, I'm going to change it to sleep 3000 and then reflash it. And it'll creep along slowly now for 3 seconds. 1 1000, 2 1000, 3 1000. And then it goes ahead and does a rapid turn. Everybody got that? You can leave yours at 75 and negative 75 and 2000. I just changed it so that it would stay in view of you. So then, clever thing that is not in the tutorials, but again, this is something that I want to add to the tutorials, is a reinforcement of the looping that we did in the pure coding tutorial. So wherever possible, I like to see, yeah, you learned the code, but now let's reapply it at every opportunity to make sure that it's well understood. And so instead of copying and pasting all this 4 times to have a big long program, sure, that will achieve forward and to the right 4 times. But another way to do it is to use the loop, the 4 in range loop from the repetition tutorial, the repetition activity in the programming to do the same thing. I'm going to paste this into my microbit first, make sure that that indentation, yeah, the indentation was messed up. So I'll indent it here and recopy it and paste it to you. And actually, I'm going to still reduce this distance a little bit. Okay. Now, it won't be a perfect square until you tune these numbers, until you tune your 75 and -75 to be straightforward. And then you'll also have to tune the amount of time that it executes the turn. I have 1150 in there. Not sure if that's really what's gonna be helpful or not. Okay, so here that is in the chat. And we'll flash that. So I have to keep on lifting mine as it goes through the 4 sequences of maneuvers, otherwise it would go off the table. So did everybody get a kind of square that we know needs to be tuned, but won't necessarily, in the interest of time, we'll skip the tuning, but can you see where this is going? Thank you, John. Thank you, Marcel. Thank you, Brian. Teresa, Amy, great job, everyone. Okay, so let's take a 5-minute break. We'll be back at 4:08. That will be, let's see, that will be 5:08 Mountain, 6:08 Central, 7:08 Eastern. And you can all feel free to either get up and stretch your legs, grab a snack, whatever, or you can hang out and talk for a little bit. I'm actually going to take a break myself this time. So
I will leave the recording going.
Thank you, Stephanie. And then we'll see you all back in 5 minutes.
Can I ask you a quick question, Andy? Oh, he's gone.
Yeah, he said he's actually taking a break this time.
Yeah, no worries. I was just looking at the code and I see that for stop, he's got bot 18.servo speed none rather than 0. And was just curious if that's an absolute versus 0.
There's a backstory to that. I can't remember exactly at the moment. I think it has to do with disengaging.
Yeah, that's what I thought, that it because 0 is positional. None is sort of like don't send anything to it. It's disconnected voltage wise. But I'd not seen that as an option previously, so I was curious.
There is reference material for the Cyberbot library he made. I will put a link in there and see if there's any notes on it.
If I were guessing, that's what my guess was.
Mm-hmm.
So I guess that means I did guess, but.
There is a Cyberbot library reference. I'll put it in the chat. It's just a quick reference.
Snagged it.
Well, I am currently rotating one of the servos around, so that way It can be just positive. Like I would honestly make my kids see what happens with the positive and negative, but I would have them talk about what they could do to possibly get all positive numbers to be positive, because then that way you can even adjust and get the perfect numbers for the perfect speed potentially. So you'd have access to one of those screws. What do you think about that?
I'll leave that to Andy to see if he's encountered anybody giving that a try.
Because you can reverse the servos. That shouldn't be an issue, but it helps the students conceptually know, or to be able to understand positive is forward. Because a lot of students, at least my students from past experience, if you tell them this tire is negative and that was positive, it gets them all sorts of confused.
Oh, sure. Yeah. The way we've dealt with that is to, I've actually stood up in the room and moved my arms around in a circle and then turn from one way to the other, just to show that they have to turn in opposite directions in order to both work together to make the robot go forward. But there is a way that you could put code on top of it and just have it be a percentage of forward or backward turning. We have another robot that uses block programming. And in that situation, I believe we have a way to set that up to just make it so it's going forward or backward without having to look at the servos in the negative value range. That's for working with the younger grades. So it is a little more subtle here. I was able to verify looking at the library reference that none is used to stop the control signal for the servos.
Thank you.
So.
Okay, how are we doing, everyone?
We're good. Stephanie had it all taken care of while you were gone.
Ah, well done, Stephanie.
No, there was.
Was there a revolt?
No, there was just a question about the none versus zero.
Oh,
and so I looked it up in the reference.
okay.
That's
And that reference that you're talking about, did you
I pasted
share
in
your
the link.
screen?
I
Okay.
just pasted in the link to it.
Yeah, I think that would be actually worth visiting. Let me see if no,
So
I'm
link is
visiting
there.
it twice.
Yeah.
Okay, so this is the reference that Stephanie mentioned. And so if we go to servo control, oh no, that's servo angle for standard servos. Here is servo.speed. Notice, first of all, that that it allows two arguments, so you can put your right and left velocities in the same call. Let's see. Here it says use none to stop the control signal. And then you can also use another _ speed call to resume motion. So by stopping the control signal, it completely, it's guaranteed that the servo will stop turning. Whereas zero, if it's drifted a little bit out of center, then that won't be as effective at stopping it. It might go slowly as opposed to being completely stopped.
Would it also, by that same virtue, mean that we're not really using any voltage. So thus the batteries, fractionally, but would last longer too.
I believe so. Yes, I believe that these servos are going to pull about 20 milliamps in their quiet. No, I tested it. It's less than that. The specs said 20 milliamps, but it's like 7 milliamps. Whereas if it's actually holding the zero position, I'm guessing it's going to pull like 40, but I'd have to measure it. I don't know.
So it's tiny. That's like half of an LED.
Yeah, but well, it'll still save batteries. So yeah, none does have the advantage of conserving your battery voltage somewhat. Now there's quite a few more opportunities here for coding lessons. So here was our right turn, and then here was our reinforcing how using the for loop that was in the basic scripting tutorials can be used to accomplish something where you have a partial maneuver, and then by repeating it 4 times, you can draw an entire square. There's a lot of other things, like for example, writing functions. A function is a piece of reusable code. And so for example, you can say that the straight function is, that should be forward really. Okay, so straight ahead is what the author was thinking. So here's forward, here's right. You could also add a backward, and here's stop with the nuns, and then straight and right. So basically, in this example, the Python runtime, the MicroPython runtime, when you load this, it's going to go, oh, forward. I'll remember it's there, but I'm not going to do anything about it because it's a definition, a def. And then, oh, look at that. Right. Okay. I'll remember that too. Oh, stop. Yeah, I'll remember that too. Whoa. Hey, this looks like a real statement. Oh, and in fact, it looks like a function call. Let's go and find the def of forward. Got to get this in both spots. Okay, let's go to that def. Do those things. And then come back and do whatever is next. And you can also do some fancier functions, like you can set it up for a duration. So, or you can even set up an even fancier function called maneuver, where you can give it the left and the right and a number of milliseconds. And what's really cool about this maneuver function is that it negates the right wheel speed, so that you don't have to keep on remembering to negate it, to do the negative yourself. You want one going forward, so it's a positive value, and the other going, or one going counterclockwise, so it's a positive value, one going clockwise, so it's a negative value. That's kind of hard to remember. So you can instead just set up a maneuver function where you end up giving it 100, 100, and then for 2 seconds, 2000. And then it takes those hundreds and that 2000, it sticks 100 here, it sticks the other 100 here, and the function itself negates it for you. And then it sleeps, does nothing for 200 milliseconds. And then once it runs out of statements, comes back here, then moves on to the next thing. Oh, it's another maneuver call, and it jumps up and does the maneuver. So these are computer science-y type of lessons that can be added. Right now, the only place this lives is in the slides, but like I said, I do have plans of adding as much as I possibly can in the time given to reinforce these lessons in the navigation chapter. There's also acceleration. By the way, I'm going to breeze through a few things here because I want to make sure we all get our whiskers going, and then I might loop back around to some of it. Okay, so the first thing is there is a piezo speaker that you can add to your board. And basically, depending on the length of the piezo speaker's leads, you can either insert it into the top if you have the long leads, or you'll need to go underneath if you have the short leads. I'm going to actually check right now which length of leads the piezo speakers currently have. Okay, so these are all the circuit parts. And it looks like the piezo speaker now has the long leads. I'm going to test that. We had short leads for a while, thanks to the supply chain shortages that have been happening. Okay, so let's see if this cinches in or not. Okay, so if the long leads work right, I can put it in the top here. No. Well, no, it doesn't really have a grip. So what you'll need to do if you want to add the piezo speaker is put it in the same socket, but from the bottom. So so putting in the piezo speaker right there.
The wheels in the way.
Yeah, it's hard to get past, but
It doesn't take too much to undo the screw to pop the wheel off and on again. We're very sorry about that. There was quite an adventure the last couple of years getting parts.
yeah, we discovered this one the hard way during a previous previous workshop.
Yeah, it went in easy.
There we go. Okay, so now I've got my piezo speaker installed. Don't worry if you don't, if you can't get this installed right now, because we're not gonna do this unless we have the time to loop back around. But basically, there is a nice set of lessons on adding the piezo speaker. And again, there are links to each student workbook page. And then it shows how to make one tone. And then it shows how to make more tones. And even in the tutorials, if we go to the tutorials, it shows how to make musical notes. And we even have Happy Birthday here, played rather rapidly. But nonetheless, we can play it. I don't know. Do you guys want to put in your piezo speaker and do this? We might have to kind of hurry at the end if we do. Anybody want to play music? I'm not getting, I'm getting kind of a mediocre response. So we'll loop back to this. The idea here though is that you can play music, and more importantly, here is a nice computer science lesson. We're using lists, which are essentially equivalent to, well, they're a little more powerful than arrays in C language, but they have a similar use, and so Python calls them lists. And so we use a list, and then there's a while loop, or you could use a for in range loop that goes through and it grabs these values and then it places them into the tone and gives you a tone where it's a note and then a duration. So that's a nice little lesson on lists that comes with the piezo speaker. Then we get to circuits, and circuits are, this is a really important chapter, but again, there's not really time based on what we want to go through. And I feel like we can all do this on our own. We can all go through this tutorial and learn the same stuff. But what I do want to point out is on the second page of this circuits workbook, there are 3 action items. First of all, go to Breadboard Basics and watch the video clip. Jessica does a fantastic job of showing you how a breadboard works. And what's really cool is that she does a close-up and shows you the little clips that are underneath the breadboard. So she's showing basically this is one of the clips that's underneath this row of holes in your breadboard. And here she's showing all the clips underneath the breadboard. She took one off of one of these carrier boards and said, okay, I'm going to pull out one of those clips. So she pulls it out and then she shows it to us and how the wire goes in that metal clip. So note that there are 5 little metal clippies that go underneath those 5 holes. Then the other action item is to consult the schematic symbols page. This shows how schematics relate to the parts that you're using. And then last but not least, we have a resistor color codes tutorial that explains how to read these colored bands on a resistor and then what those bands mean. And just a quick overview, the first digit is yellow, so that's 4. Second digit is violet, so that's 7. And then the multiplier, or rather the number of zeros that you add to those first 2 digits, is brown. And so that is 2 zeros, or multiply times 10. So you take 4, 7, and then multiply times 10. And then the 4th band is what's called the tolerance. And all of our resistors are gold tolerance, which means that whatever their stated value is, they can be off by 5%. Okay, so that was a highly fast forward of kind of the basics, and go through it at your leisure. The other thing is, what's the difference between connecting 2 wires or leads or not connecting them? Jessica talks about that in that first YouTube video I just showed you, but I'll give you a quick summary of it, which is if you're in the same row of 5 circuits here, you're connecting 2 wires together. So these are connected to each other only. These 2 are also connected to each other only. If you need more room, you can run a jumper between 2 rows of 5, and then that would allow these to be connected. Whereas, since these are on 2 different rows of 5, they're not connected. These are also on 2 different rows of 5 across the little valley in the center of the breadboard. They're not connected either. Then a little bit more about, for building circuits, understanding how those black rows and columns of sockets around the breadboard can be used. So we've got ground, that's the negative terminal of the battery. We've got 3 volts, we've got 5 volts. So those are different levels of electrical pressure that you can provide to the circuit. Then we also have some I/O pins. Now these I/O pins, you can actually write programs and connect circuits to these and turn them on and off or monitor their states. So with then it moves on to a light emitting diode. I'm just really flying through the circuit tutorial just to give you an overview before we start building some whisker sensor circuits. And again, actually as part of the homework, we'll have you go through this in a little bit more leisurely fashion if you're new to circuits. So if you take a resistor, you'll see these in your kit, and a light emitting diode, they're also in your kit, and connect it like this to a battery, electrons will flow through this direction. And then in schematic form, this is what it looks like. Here's another take on the resistor color codes. And then the idea is that you could build a circuit and connect it just to the 3 volts up here, or the 5 volts up here, and your resistor or your light would be stuck on. But if you instead connect it to these input-output pins right here, what you can do is use a statement. You can say, in this case, baud of 12, right digital of 1, and that connects the pin to the 3 volt supply. And then the other end of the circuit is connected to ground, GND. I'll loop back to that in a second. And so the microcontroller is programmed to apply the electrical pressure. Whereas in this situation, right digital of 1, turn the light on, right digital of 0 inside the microcontroller, instead of connecting its P12 pin to 3 volts, like over here, it connects it to 0 volts. And that keeps the, because 0 volts is at both ends of the circuit, there's no electrical pressure, no electrons or currents flow through the circuit. So here is an example of what that circuit looks like. So this is the in theory version of the circuit. This is the build it on the breadboard version of the circuit. Notice that we're using rows of 5, where we're connecting this lead of the resistor to this wire, and then this wire jumps down to ground. And then this lead of the LED, I'm sorry, this lead of the LED is going to ground. This longer lead of the LED is in the same row with one of the resistor leads, and then that jumps over to P12. So that's why this is P12 here. And then this script will turn that light on and then turn it off with a half-second pause between each. And in the tutorial, the students are encouraged to try different delays, different sleep values here. There's also a push button circuit. I'm going to say it's setting the groundwork for what we're going to do with whisker sensors. And then this is kind of a condensed version. But again, I'll have you guys go through this at your leisure, especially if you're new to circuits. That'll be important to go through that. For those of you who are familiar with circuits, we'll have you try a light sensor version. And so it talks about also the how and why of when you press a button, how you get a binary 1, and when you release the button, you get a binary 0. So those are all lessons that I'm skipping over just to make sure to get to the more challenging stuff. And what that more challenging stuff is going to be object detection with whiskers today. But first, I'll show you. Okay, so this is our infrared detection circuit. That's for when the robot doesn't when we don't want it to have to bump into something in order to know it's in front of it. This is the whisker circuit. This is the one we'll be building today. And these little whiskers are sticking out in front of the robot. And well, you'll see soon enough. This is a light sensor circuit. Some of you may want to play with this between today and Friday. And then this is an infrared detector that you can actually point a TV remote at the robot and drive it around. Stop. There we go. All right, so whisker circuits. This is what it's going to look like when we're built, and you'll be able to push on this whisker. It'll bump into one of the posts, and the robot will recognize that. So with that said, I would like you to grab all these parts from the silver bag in your kit. I just emptied out that silver bag in order to fish out the piezo speaker. So the silver bag looks like this. It's got this this number on it right there. So go ahead and empty out that silver bag either onto your table or out into a small bowl or paper plate, whatever you happen to have nearby to hold loose parts. And then we'll go ahead and grab these parts.
Who makes all these little bags for you, Andy? You
I
guys?
don't know. I do not know. Actually, yeah, sorry, I'm not sure who does these parts kits. With what I do, writing tutorials and etc., I don't often concern myself with the supplier I normally find a part at DigiKey and determine that it is, has a stable supply.
Yep.
If I'm designing a kit for, like this one, like at one point, I was going through and either designing or adjusting a kit, like, the What's a Microcontroller that you mentioned earlier, Stephanie, I and Tommy from cyber.org designed that kit together. And by the way,
Yeah,
right
and
now,
I
Go
can
ahead.
confirm. I can confirm we actually do those ourselves.
Wow.
So it's either Felix, Leah, or Mark. Those are the names of the people involved in putting the stuff in the bag.
Oh, Ari, I
Robin-
didn't know you were here. Thanks for coming.
Yep. Joining from Cambridge, UK, Raspberry Pi conference. So
Alright.
like midnight over here, 12:30. So yeah, it's our own stuff. And yeah, sometimes it sounds like a simple bag of components, but sometimes we had to shop around for those resistors. We use a single brand worldwide of resistors that fit really nicely, solid connection on that breadboard and the headers. And sometimes we need to source them from around the world. We get them sometimes at DigiKey US, but sometimes Hong Kong, sometimes Taiwan. And that's Robin, our purchasing that goes around the world, getting them, sourcing the right resistors. So yeah, there's a lot of work in sourcing the parts. So Andy specs, and then sourcing the parts and bagging them. So
Yeah.
So brown, black, so your resistors, this is where having your cell phone to magnify may come in handy, or having a manual magnifying glass. Because you want to make sure to get the right resistors. You'll want to get the brown, black, orange, and then the red, brown resistors. So there's two red, browns, that's 220 ohms. And then there's a couple of 10 kilo ohm resistors, that's brown, black, orange. And incidentally, I could even paste in this page for you. All right, is everybody able to work from the screen for this one? Okay. Okay, excellent. And then I'm off screen gathering them as well. All right, so I think I've got everything. How are you guys doing? One thumb up, one shaking head. Okay.
I'm looking for the 3-pin headers right now.
Yes. Okay.
The 3-pin headers are in the bag with your Piezo speaker.
And that's going to be a little black cylinder. Well, there are quite a few of them, a little black cylinder with 2 pins sticking out of it.
Ari, I'd be really interested in chatting with you when you are done with that conference. I was mentioning the same thing with Andy about how things are going over there with Raspberry.
all right, maybe after the recording ends, so we don't distract the class. Yeah.
No.
Okay, are we there yet?
Still get my resistors.
Okay,
I know what I'm doing.
I'm going to be the 5-year-old in the back seat with you guys.
I'm good now.
All right, way to go.
The couch ate a few of the resistors, but I found them.
Yeah, my floor ate a part that missed the little bowl I'm keeping them in, and I just cannot find it. I'll have to figure out what it was and then where it rolled off to.
I had a question for the resistors. So when you're saying like brown, black, orange, we're basically ignoring that gold at the end.
Oh, yes, that's an excellent question. Thank you.
Okay.
Yes, we are ignoring the gold at the end. So it's yeah. All of the resistors are going to have that gold band. And so I didn't call it out in the instructions.
Isn't that just to help you keep track of direction?
No, because resistors are non-directional. All that gold band is it's telling us the tolerance. And so one thing I wanted to show you here is most phones have a magnifying app. And so here are the resistors magnified. So I'm hoping that you guys can see that that's a red, brown. I have to say that brown looks kind of black on my camera, but yeah, it's pretty identifiable as, yeah, because there's brown, black, red. And yeah, coming through 3 cameras, it's not really, or 2 cameras, it's not coming through all that well, but looking at it with my eyes at the phone, I can see the brown, black, red. And so this is where a magnifier does come in handy.
You mentioned the couch eating a few parts. We do have a refresher pack of the electronics that's available for, get 1 or 2 for the classroom in case little parts go missing, or to just refresh between school years. I put the link in.
Oh, you put the link in, thank you.
Yeah.
So this is the electronics refresher pack. Having a few of these around just for when students lose, step on, or otherwise don't have a part. We can, having a few of these is nice for just handing them out. When I did in-person workshops, I always brought a few extra bags of these with me for that reason and used part of them each time. Okay, are we ready? Do we have all our parts? I think I'm going to take silence as assent and just somebody give me a shout out if you're still working on that. So this is how we want to oh, by the way, does everybody have on the front of their Cyberbot, did we already add these longer posts?
Yep.
Okay, excellent. Yeah, that should have been in the instructions. Great. So we already have those longer posts on the front of the Cyberbot. So all we need to do is loosen the 2 screws that hold those posts down. And then we're going to hook one of those whiskers around one of the posts above the nylon washer, and then the other whisker around below the nylon washer, and then retighten the screw. So you don't have to take the screw all the way out like this. Just loosen it a little bit and then hook that whisker in and then cinch it back down. And when you're done, we haven't done the circuit yet, but we want basically the whiskers to kind of go parallel to the breadboard and then out in front. So I will demo this. Managed to misplace the parallax screwdriver that came in the kit. Yours is going to be blue with this vintage. So all I'm going to do is loosen up both of those posts by a couple turns, and then go in above the nylon washer on one side. Do a couple more turns here. Okay, so there, I'm almost hooked in. Looks like I did hook in. Okay, so once the hook is around the shaft of the screw, just tighten it back down. And you may need to actually use a finger to hold it in place as you tighten it. So that one went above, so I'm going to put the other one below the washer, the nylon washer. Oh, I thought that would be so easy. There. You definitely need to unscrew it a little bit further than you might imagine for it to go in easily. And then hold it in place and tighten it back down. And again, we want the whisker wire to be parallel to the breadboard where it comes out of the like that. Again, the links to the workbook stuff is here. I'm going to copy this in so that you can go to that page and potentially increase its zoom on your computer. So if you want to just go here and check the circuit and possibly zoom in on it, that's one way. I'm going to leave this up like so. And now what you're going to do is carefully take your brown, black, orange resistors, plug them into 3-volt sockets up top, and then actually place the posts first, these 3-pin headers. So you'll want to place these 3-pin headers at the 1st, 2nd, 3rd, 4th, 5th, 6th, 7th row down. You'll plug in one 3-pin header. You want it to sink all the way into the breadboard so that the plastic holding the header together is up against the white breadboard. And then 8, 9, 10, the 10th row down, you'll do that with the other 3-pin header. After that, use the 10K resistors, the brown, black, orange ones, to go from 3.3 volt sockets. And these are the black plastic sockets up top. And then other end, one goes with one 3-pin header, the other goes with the other 3-pin header. Then you'll use your red, brown 220 ohm resistors, also going in the same row as a post. And the lower 3-pin header post, you'll go from a socket to P7. Make sure to get it into the black plastic header to the left of the right breadboard. There are sockets there. It's very common for students and teachers to make the mistake of trying to plug it into the white breadboard. That won't allow your microcontroller to sense the whisker connection. You got to have that resistor, that red, brown, the other end connected to P7 and P9. Another common mistake is to accidentally go up or down by one, and that'll also cause some trouble, but we have some testing to go through that. Oopsie. Let's see here. Okay, how's that look? Is that clear enough for everyone? Okay, I'll start building mine too.
We call this radio silence.
Is that the scary thing for radio stations where they don't want people to change the channel?
I don't know, man. If my classroom gets quiet like this, I start doing something weird.
Doesn't it mean everybody's engaged, or does it mean they all are secretly looking at their phones?
The answer is yes. There's secretly something.
Or they're trying not to accidentally plug it into a 5-volt port and possibly let the smoke out.
Yes,
Oh,
although
Oh,
that-
the blue genie.
yes, although you're okay. As long as you're above that, those are 10 kilo ohm resistors. And for the propeller microcontroller that's under the breadboard, as long as you're above 3.9 K, by specification, you won't let the smoke out. In practice, geez, I've gone down to like, 220 by accident, and I don't recall having a problem, but that's way below what the spec is. Sorry for the autofocus.
Woohoo.
All right, I heard a woohoo. That sounds like one person got it done. Let me see if I can get back to the.
Wait, do that again, Marcel. I caught that as possibly two different hand gestures. Couldn't tell if it was one of these. Yeah.
None of this. Okay, you're confusing me, man. All right, so how are we doing? Can I get thumbs up now that I can see you all? Or thumbs down, as the case may be. Oh, looking good. Way to go, everyone.
4 or 5.
I'm up to 8 because some of
Oh,
the,
good.
yeah, those reactions go away. Okay, remember to give me a shout out if you need a little bit more time. Otherwise, I'm going to move on here after I get a screen that you can't see out of the way. All right, so here we are with our whiskers. So next up, there's a test script, and that is right here. I'll go ahead and paste in the
I like that addition, by the way.
it's just another cool thing about the microbit. The thing is that it's just such a joy to work with in these robots.
Yeah.
After the initial pain of designing the way they communicated, that was quite a project. Okay. Which none of you will have to do because you've got the nice Cyberbot module. All right, so following, I pasted it in to the chat. And now here we are at the script page. And what's going to happen is that if you press the left whisker against the 3-pin header, it'll actually hit the right 3-pin post, but in the script, it's all accounted for. And so we'll see a light on the left or a light on the right, or if we press both whiskers against both 3-pin headers, we should see 2 lights. And so this is the test script to do that. Paste. Select all. Whoa. Select all. Paste. Flash. Okay, so now my script is running, and at this point, if I press the right whisker against the post, we see a light on the right side of the microbit. Every time it touches the 3-pin header, which is over here, it's the left 3-pin header. So the right whisker connects the left 3-pin header. Make it so that we can see it right versus left. Okay, right whisker. It's bumping into an object. So the light comes on. Left whisker, bumping into an object, left light comes on. Both whiskers, bumping into an object, both lights come on. So, and then if you back it up and are not connected to an object, we want all the lights off.
What
So
happens if one light always stays on?
that
Did I-
probably means there's a circuit error.
Okay.
So one of the most common circuit errors for that one is if, let's see, what would cause a light to always stay on? Oh, probably,
LEDs crossing.
well, leads crossing, or let's see what happens. See, if I have it in the wrong, I just plugged it into the wrong port. And so if the left light is always on, check your IO socket for the resistor on the right. So I'll unplug that, plug it in the right place. Now leads crossing will more commonly result in, well, basically go through and make sure that none of these metal leads are touching each other. So especially in this
Oh, that
area.
was it. Yeah, that was it. They were touching each other.
Oh, they
Okay.
were.
Yeah,
Okay,
yeah.
this one's yours, Alan.
I could see it from here.
I apparently so.
Yeah.
That's a less common for that particular symptom in my experience, but
It's tight when you are bringing them over from the 3.3. That
yes,
if you don't bend them just right, kind of get them out of the way, it can get the two of them to connect, which creates the circuit.
okay, so have we all got it so that each whisker, make sure those, now the other thing that can cause it is if you have a whisker that is up against the post the whole time anyway. If you tightened it but didn't leave like an 1/8 of an inch of space between the whisker and the 3-pin header, that can also cause that particular problem. So once you've got it so that you can press each whisker and have it light up on the correct side, then we'll just go ahead and do the whisker navigation. That's navigating by touch. I don't know if this one's going to be too long to paste in. We'll give it a try. Okay. See, first of all, I should paste in the page.
Slide 112 has the link.
Oh, thank you. Thank you, Alan.
You did it.
Yeah, but you called it.
Uh,
Okay, so here's the page, the link to the page in the chat. And then I'm going to try pasting in the whole script and we'll see how we do here. It made it. So you can actually just copy and paste that script into your editor. When you run this one, make sure to set your switch to 1. So before flashing the script, set your 3-position switch to 1. Then flash. And then to test this, what you can do is disconnect the USB cable, making sure to keep the microbit pressed into its socket. Then set it to 2 and give it an obstacle like your hand. It's going to go forward. And then back up. And select a new direction. So let's go ahead and all test that and make sure that you've got your navigating bot. I'm actually going to mess with these numbers and give you a modified script to flash in. Test it first. What I'm doing is having it sleep for a longer time at each speed. Okay, let's see how this goes. Yeah, that's better. So basically, if you change all those 250s to 750s, it's going to be a little bit more realistic in the way it avoids an object. I won't paste it in. It just, if you take all these sleep 250s and change them to 750s, like I did here, I think it'll perform a little bit better. So these were all sleep 250s. There were 3 of them, and just change those to 750s, and it should respond a little bit better when it bumps into your hand in terms of backing up and turning. Okay, so what do you guys think of that?
One
Everybody-
of my wheels is going forward, back, forward, back, forward, back. Is that supposed to happen?
Yeah,
Where's-
that could be again either wires touching each other. It could be leads or wires not plugged all the way in at a certain spot. So the vibration
Okay.
of the robot, if it's not plugged all the way in, which is, you know, you want it to sink 1/4 of an inch into each socket and 1/4 of an inch into the breadboard. And so those, if you do both of those,
So if it passed the earlier test though, then it
definitely
could-
something's loose.
Okay.
That would definitely be a lead that's not all the way in its socket.
Okay.
My dog is chasing it down the hallway.
Oh,
Every time it turns
that's
around,
awesome.
she jumps and acts like, what's going on?
Yeah, our cats are very stern with the robots. They always show the robot who's boss.
Now get the piezo hooked up, so when every time it bumps into something, it makes a great noise. It'll only the dog will hear.
Oh, yeah.
At
Put-
that
Oh.
frequency.
Put it up above 20,000.
Yeah.
The piezo actually filters that out. It doesn't really make much noise above, I forget what the actual value is, that the one that the microbit makes might be different. Okay, so we're short on time. How many people got that application to go? Excellent. Excellent. Way to go, everyone. Fantastic. Okay, and so we'll have some troubleshooting after the session. I gotta just run through a couple more slides before we finish off for today. What I want to mention here is that we're going to skip this chapter as far as the workshop goes, but it's pretty cool. There's some sensors in here for light following and or avoidance. And So there, as soon as he shined the flashlight on it, I'll replay that. Whoa. One more time. So it's going, then he hits it with the flashlight and it turns and follows the light. So that's one application of the light sensors. Another one that we'll have you do for optional homework, I want to emphasize optional, is just have it stop under a shoebox. You'll just follow the instructions on the pages. And so this is an example of that circuit. We'll have you build a simpler circuit for the, so this is the light following circuit right here. Again, for homework, we'll just have you do an earlier one in that same chapter where it'll stop in a dark, shady spot. Okay, so homework. First item is you'll have received a couple of emails, one from our automatic learn.parallax.com system that tells you to follow a link and set your and change your password to something that only you know, as opposed to the generic password you're starting with. And then another one from Stephanie with some additional information, again, about doing your password, and then how to go to the teacher resources and take a look at them. So if you have not already been signed up for learn.parallax.com, or if you are already signed up for learn.parallax.com, you'll just go to the login page. And I'll send these out as links. So you can just follow the link and you can enter your name and your password. And then hit login and you'll be able to get to the teacher and then follow the instructions in Stephanie's email, which you will have received during this class. So it should be in your inbox next time you check it. So you'll be able to go to learn.parallax.com/cyberteachers to get to the educator resources after logging in, as shown here. So that's one item. It's not the end of the world. If you end up having trouble finding it, maybe it's in your spam queue, maybe there was some other gotcha. And so if you already have a Learn account, just go to the user login page like I just did. If you don't already have an account, Stephanie and learn.parallax.com will have emailed you with instructions for, setting up your password and then instructions for how to get to the teacher materials. So either log in, and by the way, you might find yourself going to learn.parallax.com and scratching your head going, oh, gee, what was my login? If you don't remember your password or something like that, you can just request a new password with this button. And the other thing, sorry for keeping you a couple minutes late here, is we have some optional homework. You don't have to do any of this, but I do hope you will find, half an hour or so to experiment in one of these two areas, especially for those of you beginners with circuits. I would definitely recommend going through the circuits chapter. And in that circuits chapter, we looked at all of these. We looked at the LED circuit. We looked at the getting ready to build page. That's where there's actually 3 links that you'll want to go to. One to learn about breadboards, one to see the schematic symbols and the resistor color codes. So you'll go here and then you'll keep on going through. You'll build the LED circuits, which means you'll be taking apart the whiskers circuit. So only start this after you're done with the whiskers circuit, because we want to remove all the whiskers stuff before putting our lights on, for example. And then then you can blink a light. You can also check the push buttons and learn a little bit more about what's going on inside the whiskers, because this talks in detail about what's happening inside the whiskers. So this one for circuit beginners. And then if you have some experience, I just randomly chose intermediate. I didn't really know what the best word would be. Visible light navigation. Now, I'm only having you go through really the park in the dark activity. And so what you'll be doing is you'll be creating a simple light sensor. Initially, you'll be learning, first you'll learn about phototransistors, then it'll have you build the light sensor. which is this circuit right here. And then going to the next page, you'll get to measure phototransistor voltage. And then it's going to have you use a lot of resistors, but you'll only be using one in the circuit. The thing is, though, that what you'll be doing is you're going to measure the transistor voltage, and you might see that it doesn't give you a very big value or a very big change. Like when you put your hand over the sensor, it might not change a lot. And what it shows here is if the light in your room is really bright, you'll want to go with a smaller resistor like the 2K, which is, it was listed earlier. So it lists all the color codes on the first page. So you may want to refer back to the color codes for each of these resistor values. Then when you're measuring voltage, what you'll want to find is a resistor that makes it respond well. And so you'll actually be subbing out the resistor in the circuit you build, which is right here. So this red, black, red resistor is kind of in the middle of the range. But if it's really dark, you might need a brown, black, orange. If it's really bright, you might need a smaller resistor. So we're starting with 2K, that's red, black, red. But as you do your tests, the measuring voltage tests, you want to see a big variation when you cup your hand over the phototransistor. And so if it's bright where you are, you may want to go with smaller resistor values. Again, those were listed and their color codes were listed on an earlier page. And I think in the email, I'm just going to call those out to make it easier. Or if it's dark in the room, you may need to go with a larger resistor in that circuit. Once you've picked the right resistor, then there's a park in the dark activity, and you'll use this script and you'll put it in front of a shoebox garage and you'll have it drive forward. And if you've done everything just so, it'll park right in that garage for you. So those are the optional homeworks. I'll have you skip all these guys because that's a lot of extra work, and I know it's still the work week, so we don't want to take too much of your time. Then we'll reconvene on Friday for infrared navigation and to look at the various curricula available for the Cyberbot. Any questions before we go to the tech support portion of the offline tech support portion of the workshop? Okay, I do have one final announcement, which is that currently there is Chrome decided to, or Google decided to do some updates, but they didn't catch a bug that they cleverly hid in their operating system updates. And so currently Chromebooks are going to give a negative message when you hit the connect button. And they say that they're aware of this bug and that they're going to have it fixed by the end of the month. Now, some of you who are attending this with Chromebooks have already encountered this, and that is actually why why I showed you guys the drag and drop approach of loading code. That still works. So you can still use the, you can still write your code in the online editor and download it and then drag and drop the hex file onto the microbit, which you'll have to do since the connect button in the microbit editor on Chromebooks only. This connect button here is currently, when you click it, if you have a Chromebook with the most up-to-date operating system, it's going to give you an error. And again, that's going to go away in 2 weeks. They have a new release plan to fix the bug. And that's not on Microbit, that's on Google and their Chrome browser on Chromebooks only. So just a heads up for any of you that might be in that situation. Otherwise, that's it for today. Thanks for coming. We'll look forward to seeing you on Friday. And we'll continue without recording to do any extra tech support and or questions and answers to make sure your robots all do the whisker roaming. Thanks for coming, and we'll see you on Friday.
All right, I will stop the recording now, but tech support can continue after.